let's talk about exponential growth and decay. So exponential growth and decay is just a very specific form of an exponential function where we're actually going to be given our amount of growth or our amount of decay, but we're going to be given it as usually as a percent. So that's why we have to adjust our formula a little bit, what it looks like. So if you remember our exponential function, just the general form looked like y equals a b and x, right? A times b to the x is what exponential functions look like. And so what we're doing is a is still the starting value. That hasn't changed. X we're going to call it t instead of x, which is just, a different variable, but we're going to be a little bit more specific, and we're going to talk about how many times have we increased the function, right? So it's going to usually be a representative of time, okay? And then this middle value, the b value, we need to be more specific, and we're going to say 1 plus r, which means how much are we increasing as a percent. We're going to put that percent in decimal form, though, right? So we're just taking our standard model of a times b to the x, and we're getting a little bit more specific. Okay, so let's take a look at an example of exponential growth happening. We're going to just use this exponential growth model. So this problem, I'm giving you the formula, that same one that we just saw, and there's a situation where there's a population of deer that started off at 3,500 deer in the year 2000. Every single year after the year 2000, it increased by 3.5% annually, which means every year, 3.5% more deer were there than the previous year, and then it keeps growing from there. And so they're wondering, after 20 years, in the year 2020, how many deer can we expect to be in the population? So we're going to write an exponential growth model by saying y equals, my starting value was 3,500, so I'm going to say 3,500 is a, okay? 1 is always 1 because that's like neutral. That is when we have no increase or no decrease, we multiply by 1, right? And then the rate in this case is going to be my percentage, okay? But it's going to be in decimal form. So 3.5%, okay, we would say is move the decimal point 2 times to the left, and I'm going to end up with 0.035. So I'm going to say 1 plus 0.035, which is just 3.5% as a decimal, and I'm going to leave this to the t. So this is the function that I'm going to use, right? So I can say, simplify this a little bit, 3,500, okay? This is 1 plus 0.035, which is just 1.035. And I'm going to be specific this time. They said 20 years have passed. From 2000 to 2020 is 20 years, which means we are going to increase the population 20 times. So I'm going to put a 20 here. Okay? So now I can go to my calculator and let it do its magic, and we're going to find out what the answer is. Right? So I'm going to clear out my calculator. And I'm going to do this order of operations wise. If you're just typing it into a graphing calculator, you might not need to do this. I'm doing 1.035 to the 20th power, okay, and it gives me this pretty big number, okay, and then I'm going to multiply that by 3,500, right? So I'm simplifying the expression, and it's telling me after 20 years, I can expect, if I round to the nearest whole number, because deer are whole things, we can't have decimal versions, okay, I'm going to say that I'm going to have about 6,964 deer. So I'm going to say the final answer that they're looking for is 6,964 deer, right? So instead of us having to multiply, say 3,500 times 1.035 times 1.035 times 1.035 for every single year, we were able to just use the exponent of 20, okay? So exponential decay is the same thing, except instead of the population or the growth or the change increasing, it's just decreasing. And so the only change that we have to make to our general formula is that instead of us adding the rate onto 1, we're subtracting the rate from 1, because we're going to go down from 1, not up from 1. So you've noticed this is the exact same formula that I gave you for growth, except now we're doing minus r instead of plus r. So let's kind of apply one of those and see what happens. Okay. So, we did that. So let's talk about this one. So we're going to do a growth problem, okay, and then we'll do a decay problem, okay. So as a growth problem, again, here's another simple example. So we're going to say if we're doing a growth, okay, starting at $250,000, 4% per year, and they want to know how much money can we expect to have in 10 years. So again, there's our key information. If we want to go through and highlight, okay, we can say starting value, annual rate, right, percent of increase, right? I care about the word increase because that's telling me to use plus, right? And so now I'm going to go through and I'm going to just fill into the formula. I'm going to say y equals starting value, 250,000, okay? and I'm going to increase 1 plus 4% as a decimal, 1.04, to the, in this case, it's 4% per year. 10 years have passed, so that means 10 increases. All right, so again, I can go to my calculator, okay, as you stare at the Scrooge McDuck jumping into the to the pile of money, okay, and we're going to say 1.04, that is my 1 plus 0.04. I'm going to raise this to the 10th power, okay, and then I'm going to multiply by the starting value, which is 250,000. And there, so we can expect that after 10 years that the revenue is going to be 370,000. 0.61, and we can say 0.07 because money does have a couple of decimal places, right? And we can say that that would be an approximate value with a 4% increase, right? So if we switch now and we compare this to a decrease problem, right, it's going to be the same idea, okay, where we're going to say there's some computer system that starts off at $3,000. But we obviously know that when you buy something and you use it, that the value of that thing goes down. It's not worth $3,000 a year after you bought it. It's worth somewhat less. So they're saying that this computer system that we bought for $3,000, right? So again, let's go through and just highlight our key information. $3,000 is our starting value. I care about the word decrease here, okay, because that's going to tell me to use the minus version, okay? 15%, okay? And it says every 3 years. This is actually a slight difference, okay? So 15% per year per every 3 years, right? And they want to know its value after 9 years. So let's write our function. So we're going to say, and get my pen out, okay? We are going to say y equals the starting value, 3,000, okay, times 1 minus, and I know that because of the word decrease, and I'm going to say 0.15 because that is 15% as a decimal. Now here's where we have to be careful. We are not going to raise this to the 9th power, okay? And here's why. And you might start be saying this because of the every 3 years. We're going to say how many times did we decrease the value of the computer system if it's happening only every 3 years. So I'm basically saying we're going to decrease it at year 3, and then we're going to decrease it at year 6, and then we're going to decrease it again at year 9. And if you notice, that was only 3 decreases that happened. So instead of me putting a 9 here, that would be if it decreased every 1 year. Because it's decreasing every 3 years, I'm only decreasing the value 3 times. So be careful. That t-value does not mean years. That t-value means how many times did you decrease it by the time you got to the end. So again, let's go through and just do a simple calculation. I'm going to say 1 minus 0.15. Well, 1 minus 0.15 is 0.85. So that's what I'm going to raise to the 3rd power. And I'm going to get that answer. I'm going to say times 3,000. And so it looks like after 3 years, after 9 years, at 15% decrease every 3 years, we're going to say it is worth about $1,842.38. Okay, so there's a couple of things to be careful about in this problem. The first one is decreasing causes our plus to become a minus. Okay, and every 3 years means that we need to kind of go back and manually count how many times our decrease happened, and that is what the exponent will be.